Hey everybody, how are we doing? I think Vincent has a question to start here. Can we open up the homework and quizzes? So the homeworks are open. Vincent, are you able to do the homeworks? The homeworks are currently open and you can view any quizzes you've done to see the results on the quizzes. So all the homeworks should be open to practice. Do you have any questions on the homework? I'm gonna take a look at one thing right here in a second. But do you have any questions on the homework right now? And I'm gonna show a little 475 code, really cool. So if you have questions, let me know. Here's something for 475 starting us off. So what I've added right here, and we saw this at the end of 320 because I wanted to show them a little 475, they were asking about it, is a color picker. So this is probably one of the coolest ways to actually choose a color for this histogram. You can choose both the opacity of it, and you can choose the sliding color scale right here. You could change from hexadecimal to RGBA. You get basically, if you know, it's the same sort of thing, right? It's just telling you the code of it right there. And that's what it's inputting when it inputs the color. So we can make purple, or we can make a very see-through purple. That controls the alpha on it. Yeah, pick one, Vincent. Sure, let's do it. Say, hey, Brian, could you do this one? Or from a chapter 13, and we'll do an old homework question. So you might think this is a lot of code right here, but it's really not that much. This code right here is the color picker input. I'll drop it here in the chat. So this is the color picker input. It's going to let me, won't let me say that. Hello. It really will not let me paste this. Oh, it's over the character limit. That's why. There it is. So that's the color picker input. You can also notice down here, I basically took their code, a bunch of color picker inputs. They're using it in complex ways, but I just took one of the basic color picker inputs right here and dropped it in. They're also calling something from scales, it looks like. So what you need to go down here, and after you have something in the UI, you need to connect something in the UI to your server. So if you notice right here, we have the, and I was making a mistake when I was trying to use this earlier, you have here input ID 2. That's because up here, this is ID 2. So maybe I'll call this hist color or something like that. Down here in the bottom, this would need to be hist color because that's in the input list. And so we would see right here. So what we could do is we could make a second color picker input. Let's just grab this right here and then we'll check out some more 201. And we'll put a second one right here. A lot of code is copy paste. Awesome. About another problem that I may have with, oh yeah, Mark, let's take a look at that. We might look at that after here. Let's go here to border color. And pick a color for your border. I wouldn't consider these awesome features, but it's just kind of neat. I like doing this kind of stuff. So border equals input $border, and let's check it out. And now we have a border color, and we have a histogram color. So we got to go with the histogram color of, can we actually type it in? Oh, look here. FF8200, and there we goes that. And then is it, oh, I always forget this one. It's like 880088 something. That's fun right there. But we can make whatever we want color wise. I'm trying to remember what gray is. Is it? Oh, it's something like 828800. I don't remember what gray is. So we'll take a look right here. But now we've got like mustard color. So you can then use any sort of colors you want right here on this, and pretty easy to make and change colors. But all this was added pretty quickly, and it just takes those little bits of coding. If I am to tell people one thing about coding, it's never try to sit down and do it all at once. Try to sit down, just take a moment, code something, get it to work. If it doesn't work, put it on the shelf, and then come back to it, because there's going to be errors, there's going to be problems. We could add in more features to this. Just change around the histogram. I'm trying to think what, does histogram have line width? Line width equals 4. Let's see if histogram has a line width argument. Oh, I think it does. And then I'm going to go check out another question right here. That's not a line width. Let me get the histogram. We could change something else interactively. No, it doesn't look to have line width. There's all the arguments for histogram. Oh, gray is, oh, Sam, thank you so much. Sam knows some UT gray right there. Sam, 100 points right there. We're going to have him do something different in a second. Sam, thank you so much. Sam knows, and UT orange is FF8200. That's UT orange. And then Sam knows gray right here. Sam, thank you so much. There's gray right there. And there we go. There's our UT histogram right there, displayed for data. And yeah, this is displaying the data right here that someone has. And yeah. And we could even have someone pick a variable we want. What's really neat about this, I'm going to do one more thing, I think, with this, is if we want to change what data is being used right here, let's do the following. And I love this. So Sam, if you, I think you're in 201, Watch this, Shiny Widgets Gallery. And that's currently loaded, I think. So this will allow us to take code from it, and we could actually have somebody select certain things right here, like a variable they want to show. So this is a select picker right here, and look at this. If we go to, whoops, where'd it go? What did I just do this? Oh, wait. Did I just break it? Let's rerun it. This allows us to pick code right here. And let's take it and run the code. And here we want this. Show code. Here we go. Oh, it has more examples. Now, we can take literally this picker input right here. And we're just going to take it and go up here and just drop it in at the very top. And then after it, we're going to put a comma. And guess what we've just done? Like, you'd be shocked. We now have this right here. See how it says with plain HTML? So now we have this whole thing right here with these different pickers. And let's change what it is really quickly. It's reloading the app. We're going to just do this one little thing. So this is for 475. That Shiny Widgets Gallery is amazing. It's doing an S print there. Whew, a little complicated right here. Let's say select your variable. Select your variable. And let's go to paste. And we're just going to take, we're not going to use this right here. It ends right here. And let's go to call names empty cars. Empty cars is a data set, and does this work? Please work today. Oh, and look, oh, we got other things. There's our variable names. So it's having the other variable names in there. Select your variable names. Oh, and then you see right here, we've got the other things. So we want to take this right here for the choices. Content right here needs to be only those. This is crazy code. It's crazy. I think that'll fix it. And now let's see. I think that, yes. Oh, it's double doing it. Oh, we could worry about that here in a moment. It's double doing it. Badge danger, multiple equals true. Select your variables. I don't know why it's double doing it. I'll have to go back and look at that. What chapter is the decision tree part? We could do decision tree after this. Would you like to, it's just its own chapter. Would you like to do some decision trees, Vincent? We can hop in here and do that next. This is just for 475 right here, explaining how to use this. And that Shiny Widgets Gallery is a huge help. Because now what we should be able to do is we should be able to go down here. And we should be able to go to a histogram of empty cars. So let's go to empty cars and go inside of empty cars and take input ID8. I hope this works. This is the big cross your fingers moment. And X, oh, they're already storing X right here. Oh, so wait. They're already storing X right here. And so now we want to take and store that. And we can just circumvent the whole thing. So let's see if this works. Oh, it says from must be a finite number. To from an input bins $1. Let's go right here. Min from this to 50. It's mad about the from right there. We might have to come back and look at this. X must be numeric. Oh, so it's not taking the X right there. Okay. Oh, because, oh, I think I know. So wait, should we just go as dot character? As, or let's go get. Will that work? There's always a small issue. Nope. Invalid first argument. Oh my gosh. I don't know, my app is double loading. That's interesting right there. What I should do is I should store a reactive. Last thing we're going to do right here, and then we're going to hop to some 201. What I should do is I'm going to go outside of this. This is where things get a little complicated. We're going to go with a reactive variable right here. And the reactive is going to take the reactive value right here. And we're going to store this as capital X. Or we can store it as lowercase x. Because if we store it as lowercase x, we just need to change the way the x's work. So now that's a reactive x. We're going to remove this out. And then we're going to get the min from the reactive. This should work, I hope. And then we're going to go right here. We're going to cross our fingers. You make too many changes, things break. From must be a finite number. So it's still mad about that from. And this is the to and from. 2, 0, max 50. X must be numeric. So it's not seeing it as numeric right now. This is where we're running into the problem with the data. Can we do something for chapter 12? Yeah, you want to do chapter 12? What would you like to do? Something like chapter question 5 or 6 on the homework? Yeah, let's do a chapter 12 question here. Why is this getting mad? Is that not the right input ID? Input ID, this. Input $ that. So it should be 2 seconds. Let's do this. Go here to empty cars, pipe through, select, and select input $. Oh my gosh. Last try. We'd have to come back and look at this. That would, I think that would work, because that's only going to select that column right there, but it might only make it as a data frame. X must be numeric. It's still mad about that. We'll take a look what's going on, but we'll come back to that. That's the fun of coding. Sometimes it works, sometimes it doesn't. It's mad about that reactive X. I need to see what that reactive X is, because, oh, input. That's not coded correctly. X must be numeric. It's really mad about that variable type, and it's running it twice. Oh, is it running the shiny widgets? Well, let's go take a look at some chapter. Let's hop back to the main screen. So some chapter 12 probability. Let's do some chapter 12 probability. So this is a big review of chapter 12 probability. I want to see what's going on with that app. If code's not working, I always want to fix it. I'm like, what's going on with the code? Here we go, chapter 12 probability question. Let's do it. So one of the hardest problems are the chapter 12 at least one problems. So chapter 12, please take the review of it. Make sure to practice these questions. But these are some of the problems that are the hardest for people to solve. So when I talk about at least one problem in probability, we're saying like, what's the probability UT wins at least one game this year? So historically, UT wins 70% of their games. How many games do we have in a season? I need your help right here. With a blank game season, what is the probability UT wins at least one game? So think about this right here. How many games? 12 games in a season. What are the two scenarios? What are the two possible scenarios? The two possible scenarios are what? UT will either do this or either do this. There's two scenarios. And this is how I write these out. Correct. I think you're right. You're on the right track, Ditto. So there's two scenarios. Scenario one is they will either win at least one game. So we have a scenario here. Win at least one game. They'll win at least one game. Or what? Or they'll, and so you're correct. And how would you say that? They'll win at least one game, or, and you are correct about the no games, but explain that another way. If we don't win any games, we what? So if we don't win any games, we what? You are correct. If we don't win any games, we what? If we don't win any games, we what? They're on the right track. How could I also describe not winning any games? We either win at least one game or we lose all games. So would you agree, and people should agree with this, that one of these two things must occur? But when I say or, one of these two things must occur. So when I say or, what am I doing to probabilities? These are disjoint events right here. They're also complements because either you win at least one game or you lose all your games. One of these two things must occur right here. One of these two things must occur, which is one. And they're complements because either you win at least one game or you lose all your games. These are disjoint because there's the scenario where we lose all the games in the season or we win at least one game, which we could win all our games. This win at least one game encompasses a lot of different things. You could win 2 games, 3 games, 1, 4, 5, 6, 12, 8, 9, 10. They add up to 100% exactly. So this is everything that could occur. You either win at least one game or you lose all your games. They both can't happen. You can't say we won 5 games and we lost all our games. You can't have both these things occur, i.e. they're disjoint. So with this right here, how could we solve for the probability of winning at least one game? I think this is the best way to solve these. If you write this out and you have to, this is the steps right here I do to solve these every time. How could we then solve, and I'll help you out because whenever I say or and we have disjoint, you would take right here and add these. So the or means we can add them, or we're going to attempt to add them if they're disjoint. Disjoint means if one happens, the other can't happen. Like making an A is disjoint of making a B. If you make an A in the class, you don't also make a B. It can't happen. So there's disjoint events. When something happens, the other ones can't happen if they're disjoint to it. Visually speaking, always think of a Venn diagram. When things are disjoint, there is no connection to them. But if you have events A and B and they are not disjoint, then you will have a connection where A and B can occur. So when events are disjoint, you'll see that A and B have no occurrence at the same time. So how can we mathematically solve now for the probability of winning at least one game? What is the probability, mathematically speaking, of winning at least one game? Because now that we know they're disjoint, we can say, oh, well, we can add them because you can't win at least one game and also lose all your games. There is no overlap between them. They are disjoint, which means addition applies to them. We can add them. So how can we solve for this now? Now it turns into algebra. So how do we solve for win at least one game? What will that be mathematically? So now we want to mathematically solve for win at least one game. What mathematics can we do? Oh, I'm on top chat. Dang it. No one said anything yet. Get the hiccups. How can we solve for win at least one game? Our goal is to solve for this right here. We want to know the probability of that. So how do we solve for that? That's what we're interested in. So mathematically, what would we do? It's a solve for close N8. Close. But not, I think, close. Well, so just write it. The next step is to just write it out and solve for win at least one game. The next step right here is to write it out and solve for, like pretend this is Y. Here's a hint. Solve for Y. Does it make more sense if I write it this way? This is just Y. This is X. Y plus X equals 1. So now solve for Y. So does that make sense right there? So just solve for Y. Think of this as X and Y. Solve for Y. So just write out the equation. Remember, if I write it, it's good, but if you write it, it's better. So solve for Y. How can we solve for the probability of winning at least one game? And I think N8, you'll see it here in a second, where it's a big error, but it's a small error. Exactly. N8, great job right there. We're going to go, the probability of winning at least one game is equal to 1 minus the probability of this right here. Does that make sense? We're just rewriting the equation right here that with the probability of winning at least one game is equal to the probability of everything but losing all the games. And so now we have to ask, what is the probability of losing all the games? Well, let's just think about it. What happened to our first game this season? I don't know. If we lose all our games, what happens to the first game in the season? The first game in the season, we would what? The first game in the season, we would what? Right? Oh, if we lose all the games. If we lose all the games, we might have won the first game, but if we lose all the games, the first game, we would what? We would lose, because we're solving for this round. We're trying to solve what is that probably would lose. And then we'd lose, and then we'd lose. When I say and, what am I going to do these I'm going to multiply them. When I say and, I'm multiplying. How many times are we multiplying 30%? Because 30% is the probability of lose. There's win. Win equals 70%. Lose equals, we're saying you either win or lose. There's no ties here. You either win or lose. So, I'm talking about the season, yeah. So I hate the color change in pens. And so right here, I think you might see it, N8, where the error was. Well, careful. Not times 12, because what does that turn into? It's just the way the problem is described. This problem says that UT wins 70% of their games. So what's the probability? Just they lose all 12 games. Well, that's what we're solving for right now. This problem just states that winning has a 70% probability, thus losing, if we're saying losing is the complement of it. As long as, I think in college football, you only win or lose. So you either win or lose the game. But in NFL, you can tie, I think, still. Unless they change that again. They change things every so once in a while. And then, Vincent, you are correct. It's 0.3 to the 12th power. Be very careful if probabilities exceed 0 or 1, there's an error that's been made. So it's 0.3 times 0.3 times 0.3 times 0.3 times 0.3 times 0.3, which this is equal to 0.3 to the 12th power. So the probability of losing every single game right there is you lose all your games in a row, and that'd be 0.3 raised to the 12th power. Is this... Yeah, you either win or lose. Yeah, college is still win or lose. NFL, like 2011 or so, they made a tie. 20, maybe 20. Yeah, I think around 2011 they made a tie in the NFL. And so, yep. And then just it's to the 12th power, because if you multiply it by 12, it escapes the 0-1 boundaries of probability. And so, does this make more sense right here? It's super unlikely. Like if you do this, you'll get a ridiculously small probability. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it's virtually impossible. So the probability right here is like the probability we win at least one game. That's why, like, even if you're a bad team, like it's very hard to lose every game in a season. You got to really try. We aren't Vandy. It's very hard if you're historically 70%, but you might say, well, is it random? Yeah, it's the assumptions that we're still like 70% on any game. If we are 70% on any game, it's virtually impossible that we will lose every single game. If we truly go into a game with a 70% probability, but it's kind of, that's what's going on. Let's do one more, at least one problem. So I think these problems get easier and easier the more you do. What doesn't get easier and easier the more you do? So we're going to do another problem right here. Basically the same sort of idea. Can you go over the one that has multiple parts, like the car question on the homework? Yeah, we do a car question one, yeah. We'll do one similar to the car question here with at least one, but let's say you have 4 cars. Car question has 2 cars. We're going to do 4 cars. So here's a car question with at least one with 4 cars. Let's go take a look at it. All this stuff here. Let's take a look. So this is a Chapter 12 probability review problem. Chapter 12 probability review. Advanced auto problem. Shouts to Advanced Auto. Are they good? I think so. I think they've helped me out. I think the ones that loan you parts. Shout outs. So this is an advanced auto problem here. We're going to have 3 cars. I changed my mind. So you own 3 cars. Each car is independent of the other car breaking down. The probability that a single car will break down is 10% in a given year. Okay. Sure, what's it meant about? Each year, sure. Draw out the sample space of how your cars could break down. Okay, so this is a very complex question, but let's just think about it visually here speaking. What is a really good scenario to you with your cars? Like what is really good right here? Just visually, what would be really good? Like for you own 3 cars, and each car has a 10% probability of breaking down. What is a really good thing right here? And each car is independent, assuming this right here. What would be a really good thing? If you assume independence, you can multiply things together. That is the multiplication rule. If we assume that one car breaking down would not influence another car, which you might argue, well, wouldn't you drive the other cars more? So we're just assuming independence. Since we assume independence, we can multiply together, but what would be a really good scenario for you right here, which you would want, is what? What would you really want? What problem? What would you really want? What would you want? We're just starting with the sample space right here to say, well, this is a scenario right here where what? Who knows? What scenario would be really good for this? Like, when you think about the sample space is everything that could occur. The term sample space means all possible things that could occur. So what is the best thing to occur? What is the thing you'd be like, yes, good, it's a good year. Shout out to a good year. You'd be like, this has been a good year. What happened? Use the color coding to help out. This is what we're doing right here. This is what we're doing right here. So what would be a good thing right there, Vincent? This is exactly what we're doing. And it's important we can see the problem in like a different light because exam problems won't be exactly like my Pearson, but this is similar work right here. So what would be a very good scenario? Think of this right here. Just think of it as like you actually own 3 cars. And what would be a really good scenario for you right here, which we have visually color shown right here. None of the cars break down, right? You own 3 cars. So your first car does not have problems. And your second car does not have problems. And your third car. Please write this word in the chat. When I'm multiplying things together, what am I saying between them? When you hear me multiply things together, I'm assuming independence, and what word am I saying between them? I'll say it again. My first car did not break down, and my second car did not break down. These are cars if you can't tell. What word am I saying between the cars right there? These are cars. I'm saying and. New York accent. Now, what would be a very bad scenario? A very bad scenario would be what? And then we could solve for the probabilities of these in a second. A very bad scenario would be what? Great job right there, Vincent, and NA. Good practice. A very bad scenario would be what? These are my cars. They all break down. Can you solve for that probability? I'll let you think through it for a moment here and solve it. So who knows that probability of every single car I have breaks down? All my cars are breaking down. Sad day for Brian. Every single car he had broke down. Which is unlikely. Very unlikely. What is that probability over there? I'm going to solve this green one first. Is it that? Is it? Find out. Yep, there we go. Exactly. Carry the decimals on the other one. 0.1. There we go. Cool. Brian can math today. Plot twist. So that is the probability of multiplying those together. Those are your 3 cars. Now we get into interesting scenarios right here. So we have right here, we've already been solving some of these numbers. We have right here the probability, let's put event, break. So we have here the probability 0 cars break down, 1 car breaks down, 2 cars break down, 3 cars break down. We've already solved for the probability that 0 cars break down is this right here. And we have for the probability that all your cars break down is this right here. What is the probability right now that your cars will need some repair? So now we're literally jumping back into the other question. So let's say amount repairs. Makes it easier to understand. We'll put number repairs. What is the probability that your cars need some repairs? Can you use this? You should be able to use this table right now to figure out the probability your cars need some repairs. You should be able to figure out the probability here your cars need some repairs. So take a moment, see if you can solve it. What is the probability your cars need some repairs? I'll give you a hint visually. That's your hint visually. Visually, that should be a hint right there for the probability your cars need some repairs. What is the probability your cars would need some repairs? Because it's everything but your cars not needing repairs. So it's going to be the complement of that. What would it be? Got it. The probability your cars need some repairs. Very close. Carry the last decimal. Carry the last decimal. And 8, that is correct. Carry that last decimal. It should be 1 minus this. It's just the other side of it. Remember, your cars will either need no repairs or your cars will need some repairs. It's just this has to add up to 1. Those probabilities in the full table have to add up to 1. So when we look at this right here, we would say your cars either need no repairs or some repairs, and the probabilities have to add up to 1. Great job right there, N8. So how would we find the other probabilities? Now, this goes a little bit beyond the test maybe, but it does apply a little bit. It's a little bit complicated. How many ways, this is a more advanced way, how many ways could one of your cars need repairs? How many ways could one of your cars need repairs? And I'll show you why this kind of applies to our test. This would be probably the toughest problems we could do. How many ways could your cars need 1 repair? How many ways could your cars need 1 repair? I've drawn it out. Remember, purple means your car needs repairs. So how many ways could your cars need 1 repair? So you've got 3 cars. How many ways could one of those cars need repairs? We've got it. Does it make sense visually right here? Think of the visual right here. So how many ways could your close, that is very close N8, not raise to third though? Because let me say it to you this way. It could be that your third car needs repair, or your second car needs repair, or your first car needs repair. So does that make sense? It could be that your third car needs repair, or your second car needs repairs, or your first car needs repairs. What am I doing by saying the or word to these? When I say or, like these are the possible scenarios right here, I'm saying either your third car needs repairs, or it could be that your second car needed repairs, or it could have been that your first car needed repairs. This is a much longer solved problem. It's a good review of everything. So I'm saying there's possibilities right here. I'm doing addition because it could be the scenario that your third car needed the repair, or it could be the scenario that your second car needed repair, or it could be. So it's not getting close, Logan, so close. Logan, thank you so much. Logan, very close. You're on the right track. And they're disjoint because it can't be that your third car was the only one that needed repair. Also, your second car was the only one that needed repair. These are instances where over the course of the year, your third car needed repairs, or it was the instance that your second car needed repairs. It can't be that both of these scenarios occur. So with this right here, what would be the mathematical probability for the first car was good, the second car was good, and the third car was good? First was good, and second was good, and third was good. Go back up to here, how we do this. What is the mathematical probability for this one thing right here? For the first being all right, the second being all right, and the third being all right. I might need to zoom in really big right here so we can actually write the numbers. Oh, it's going to be the hardest thing I've ever written in my life on that. So what would be the mathematical probabilities over here? I might be able to do it. Oof, oof, oof. What would be the mathematical probabilities? That looks too big. So remember, the probability your car does not need repairs is 0.9. Oh, really? So that's for all good cars, but this is one of the cars needs repairs. Does that make sense? The first car did not need repairs, the second car did not need repairs, the third car did need repairs. And then we're adding these together right here. Does that make sense? So this right here is technically, and I'll show you the mathematics, this right here is technically 0.9 squared times 0.1, and then we multiply by 3. Why are we multiplying by 3? Because that's actually addition. I know that sounds super confusing. You're like, but you're multiplying. But you're just adding it 3 times. Multiplication is the same thing as adding 3 times. So this equation I just wrote right here is the equation. The order of the multiplication doesn't matter. This is about as complex as I can go on any of these questions. Like we're doing an upper level question right now, like the most difficult way of doing it. And I think NH solved it right there. You know what's really cool about this? If we solve for this one, which I think NH's done it, I'm going to double check the work. Let's go right here and do 0.9 times 0.9 times 0.1 times 3. And now guess what? Do you know what? This is the most utterly complex question I could possibly do. I do not expect questions to be of this complexity. If you understand this example very well, you are test prepared. Now here's a good test question. Are you ready? What is the probability 2 of your cars break down? This is a very good, very relevant, I would say, level 3 or 4 out of 10 test question. It might be, how did you get that? And then we'll talk about the 0.9, 0.1 here in a second. How did you get that probability right there, N8? How'd you figure that out? And then we'll go back and lay that here in Vincent in a second. How'd you get that 0.027? What do you know about this table of all the sample space of events? What do you know about that sample space of table for the events of your cars breaking down 0, 1, 2, 3? The sample space must be what? So what N8's doing, I assume, is they're taking and adding to these. Oh my gosh. They're adding these up. Let's add them up properly. This is a very, very, very fair question. Exactly. Does that make sense? So this last probability has to add the table up to 1. So whatever this is has to complete the table. So this one right here is 0.027, which actually, interestingly enough, mathematically, I'm just going to write the quick notation of this. We're not going to go through the steps again on this one. There's 3 ways your cars could break down 2 times. And so it would be this one right here, 0.1 raised to the second times 0.9 raised to the first. That is not really test relevant, but we went through on like a much deeper level. But it's the same sort of mathematics we used up there. And we can go right here and take a look and solve 0.9 times 0.1 times 0.1. There we go, did correctly, I think, times 3, and there's the probability. The way it was done right here is much more test relevant to say you do not have this value, and then what would it be? Let me ask you another question. Last question, then we're going to look at how these probabilities were calculated again. What is the probability that your cars will not... What is the probability that... trying to say it in a way. Oh, thank you. Tell it, Colin. I love it. You always bring that positivity right here. What is the probability... If someone said, I'm really worried about all my cars breaking down, and you said, well, the probability of that not happening is this. Just speak to me like, be like, don't worry. Like the probability of all your cars breaking down is very unlikely. The probability that won't happen is this. What is the probability of not all your cars breaking down? Like you won't have all your cars break down. What is the probability that all your cars won't break down on you? That they won't all break down on you? That at least one car will be working. That's a better way of saying it. Yep. Great job, Logan, right there. So that's the probability of at least one car working. You don't even need these other probabilities right here. These probabilities will add up to 0.99, but you could just solve it by doing one. So probably a better test question might be, like to go back, and we'll take a look at the probabilities again. Probably a quick way would say, what is the probability you have at least one working car? So the probability of a car breaking down is 10%. The probability of a car working is 90%. What is the bad scenario right here where we have no working cars? Explain to me the bad scenario, because we have 2 scenarios again. We're kind of doing the classic solve on this now. We have 2 scenarios. What are the 2 scenarios? So we have the probability of a good car is this. And let's write our 2 scenarios here. And just see the solve one more time. The 2 scenarios are... Trying to get it so I can like show it. Oh, really? What are our 2 scenarios? We want to have at least one working car. So our 2 scenarios are going to be what? We want at least one working car. Either this or this. There we go. At least one working car or no working... Exactly. We will have at least... one working, or we will have no working cars. That'll equal to 100%. Important to know this right here. We will have at least one working car or no working cars. Do you see... that's the more complex. We might go back to that here in a second, Vincent. Good question right there. Do you see what the probability of no working cars is? Have you solved for the probability that none of your cars work? And then we're going to look at that here in a Vincent second too. Do you see the probability that none of your cars work right here? Like, what is the probability, like, your first car breaks, your second car breaks, and your third car breaks? Do you see that right here, where the probability that none of your cars work? And now I'm going to go back and review the table down there, Vincent. Exactly. It's this probability, right? This is the probability all your cars break, no working cars. And so now you just algebra this over to the other side. We're just going to algebra it over back to this side. And that's literally going to solve to the probability of at least one working car. And then we visualized it down here to show the full sample space. This right here, Vincent, is a little more complex. So don't worry if this doesn't, like, this equations are not equations we'll be using. Like we said, once again, right here, I'd prefer you to be able to know how to solve for this number when it's missing, to know that the sample space adds up to 1. The reason this is being solved over here this way with these numbers is when you solve for the first car works and the second car works and the third car does not work, you're doing what to these probabilities? If you solve your first car works and your second car works and your third car does not work, you're doing what to these probabilities? So the first car works, and the second car works, and the third car. Do you know how many questions for each chapter? 7 or 8, maybe? It's like 40, 45 questions on the test. What are you doing when you say the first car works, the second car works, and the third car works? Nice job, Vincent, right there. Yep, you're multiplying, right? And then the reason we times by 3 is we're actually adding them. I know that's multiplication. This got a little more complex. This is actually the multiplication and addition rule right there. This is about one of the hardest problems to solve that we could do. We like to do we did kind of a pretty difficult question. Now we did a super difficult question. We got time for a little bit more. I'll put those questions in the chat. Let's do more problems. That was a pretty tough problem. That is if you understand the problem 100%, you can go through and map it like I did, then you're going to be able to solve all the probability problems pretty well, I hope. That was a tougher problem. Like, just make sure you map it out, you draw it out, think of it as actual things. One more question. How do we get the 0.9, 0.1 when you're given... so remember, the car has a probability rating of 10%. So the 0.9 is either your car breaks, 10% probability, or it does not break, 90% probability. Does that make sense? And then when we do the 3 cars, we're saying the first car worked, and the second car works, and the third car works. So we're doing 0.9 times 0.9 times 0.9. If you're doing 3 cars break, it'd be your first car breaks, and your second car breaks, and your third car breaks, 0.1 and 0.1 and 0.1 multiplying together. Does that make sense, Vincent, right there? So the 0.9 is the probability that a singular car works. The 0.1 is the probability that a singular car breaks down. And then we can multiply those to say what's the probability the first car breaks down, the second car breaks down, and the third car breaks down. So it's open floor on questions. Let me know. What do we have? Thank you, Vincent. Great job, Vincent. 100 points. Keep asking those questions. It's all communication right here. Yeah, Lakeisha, let's do that. Let's do some review of notation. Yes, I think we went over it during office hours, and we've gone over it during some of the classes. So last night's homework and quiz were gone over, like the waiter and waitress problem, stuff like that. Check it out. Let's go do some sample surveys. Doing pretty well today. Yesterday was a fun day. Yesterday was one of those days.
One of those crazy days.
Yesterday. My fiance said, I hope today's better, and I said it will be. I had to deal with not fun things. So let's do sample surveys. I don't like certain parts of my job. I like the parts of my job that are fun, like talking about sample surveys. Talking about some randomness. Kind of parts of my job that I love right there. Let's talk about some sample surveys right here. And this is all about those notations, no cards. So let's take a look. Oh, you pulled perfect Darkrai. 15, 15, 15, 100% IVs. N8 shout out right there. 100 points for that 100 IV Darkrai right there. Oh man, I want that perfect Darkrai right there. Man, I'm trying to battle league it up. That's what I do before going to bed, and I'm like a little bit of battle league. Okay. We need those no cards out. Let's get serious here and start working on those no cards. And we need to know things like response bias. Response bias is going to be when the response someone gives is altered by the way the person giving the survey acts or the questions. So response bias is literally what it sounds like. It's when the bias is in the response. When people ask you, like, how much income do you make? And you're like, 2 million. I don't know. Response bias is literally when people's responses are not accurate. A lot of social survey questions, when you ask people like touchy topics like religion, politics, all those things can be a little iffy on how you ask them and how people respond. And so you'll oftentimes see people like the response is not accurate to what they actually think. And that's response bias. Classic stuff being things like, I'll just use my classic example. Is it fair that 18-year-olds can go to war, but they can't drink a beer? Do you think we should lower the drinking age? Well, that's eliciting response bias. I'm trying to get you to say, no, it's not fair. We should lower the drinking age. The only thing we should ask right there is, should we lower the drinking age right there to 18? You don't put some sort of preface in there to make someone respond a certain way. The other thing we have is non-response bias. Non-response bias is also what it sounds like. Non-response bias being Non-response bias being people who don't respond differ in their responses than those differ in their responses in a significant way than those who do respond. So once again, it goes to more like touchy topics too. If you are out there asking like a religion survey and people are coming up to you because they're very interested in religion or they have strong views, you're going to get a little bit of voluntary bias. But the people who are not responding are the ones eliciting non-response bias. So non-response bias is like you're doing a survey and people are like, I don't want to talk to you. It's like when you get a call on the phone, they're like, hey, we'd like you to do a survey, and you say, nope. That's non-response bias right there. Hanging up the phone on someone who calls you to do a survey is non-response bias. Now, what we would see is the people who don't respond have some sort of differing opinion that is not well represented because they're not responding. So you'd have to say, well, like, are the people who are not responding causing a bias? Maybe we're calling people to ask them, do they trust the government? And so people who are less likely to talk to us and respond might be less likely to trust the government and be like, well, probably not going to get good results on asking people, do they trust the government, by calling people up on the phone. And we're going to get a lot of non-response bias, which is going to be the people who don't trust the government are going to be less likely to talk to us. Like, wow, everyone who talked to us on the phone trusts the government. So I'm not saying you should or shouldn't, but if you talk to random people on the phone who ask you questions, I don't know, I used to. Back in the day, 2000, you call me like, hey, I got a survey. Like, hey, what's up? I'll tell you everything. Nope. So back in the day. Voluntary bias. So the difference right here between the two is very subtle. People who volunteer generally have stronger opinions than those who don't volunteer. So you think about this, you're doing a survey and you say, hey, let's talk about some religion and politics. And people are like, oh, I'd love to talk to you about that. Well, it's not that people are not responding to you now. It's that the people who are talking to you have a much stronger view. They're like, oh man, I want to tell you everything I know about politics. Oh man. And you're like, you're not like the normal person. And you're like, I'm Brian Stevens. I'm not normal, of course. So voluntary bias is when you generally see these people and they're not representative. This is the issue with any of these, is that we're not getting a representative view of the population. Next one we have right here is convenience. Let's give it a try today. Convenience. I didn't even get close today. Convenience bias right here is going to be sampling in such a way that is very easy to get the observations. Taking the first 100 or putting online. I see a question right here. Will there be questions about this true false? It could be true false, could be matching. If there's an incentive involved for completing the survey, is it voluntary bias? Yeah, I think that could elicit some voluntary bias when there's an incentive. That's not going to be like non-response. That would be like, these are just different types of biases right here. So I think Lakeisha, great answer right there. Logan, you are correct. These would be true, false, matching. Like, is this a voluntary bias? And these are kind of my definitions. Once again, it's not important to memorize definitions. It's probably better to memorize examples. Like thinking about if you wake up in the morning, you're like, I have to survey 50 people. Hey guys, Instagram, can you fill out my survey? Whatever, I'll give you $50. Well, now you're creating like a convenience voluntary bias. So you're having people volunteer their responses to you. It's convenient because you're doing it so quickly. More maybe of a convenience bias. You're reaching out to the easiest people to access. So you can think about like examples with this. Is this more of like an easy way of collecting data? Do I have problems that people are like, oh, I want to take your survey? Oh yeah, we'll do that right here. A systematic sample? You bet. We'll get to that next year with the different types of sampling method. Systematic coming up here soon. The last type of bias right here is going to be the undercoverage bias. Undercoverage bias is when we leave out a certain group or voice in our survey, not enough representation. So I always like to use like politics again for this. Systematic sample. And so undercoverage would be something like you go to the college Republicans and you say, who are you voting for? Well, I mean, you'll get a view of who the college Republicans are voting for, but if you want to understand like UT students, that's not going to be representative of UT students. You would want to take accordingly to the percent of the populations, which is some other things we'll talk about here soon. So undercoverage right there. Knowing the interpretations is a huge help. Sometimes we ask like, what is this? You're like, is this? Like we give you an interpretation and say, this is, like voluntary bias is when people don't respond to your survey or something. I'd say putting on flashcards can help, and then knowing examples is a big help too. So let's go here to sample methods. So the different type of sampling methods right now are going to be, probably the easiest one is a simple random sample. First step for a simple random sample is to do what? Non-response bias is people who don't respond. So undercoverage bias would be like only talking to on-campus students, but non-response would be like people walk by you when you're giving the survey and they don't want to talk to you because they have to like get to their car. So on-campus students might be more likely to talk to you. So undercoverage. Oh yeah, we'll do some interpretations here too if you want. We do it here at the end. Does that make sense, Lakeisha? So just to go back here briefly, real quick again. Undercoverage is when we don't get enough of a certain group. Like it's more of a problem the way we set things up. Like we go to the residence halls to talk to students, and you would say to me, Brian, you undercovered off-campus students. Does that make sense? So yeah, so if we went only to the residence halls, you'd say, Brian, you have some undercoverage bias. It's not that the off-campus students didn't want to talk to us or the on-campus students were really excited to talk to us. You might say it's a little bit convenient to go on campus, but the convenience bias might also be creating an undercoverage where we don't have enough off-campus students. So by going to the residence halls, which might be a little bit convenient, we're going to undercover off-campus students. There wouldn't be any off-campus students. We left out a certain group in the way we did our survey. It's not because they didn't talk to us. It's not because they gave us a weird response by the way we worded our questions. And it's not because they're like, oh, we want to talk to you. It's just that we went to the dorms and we didn't have the opportunity to collect these students. So just kind of think of which ones it would apply to. When we go here to the sampling methods, who can remember the first step for a simple random sample? What is the first thing we do when we do a simple random sample? First thing we do. Everything gets a what? Simple random sample. Everything gets a what? Everything gets a number. Logan, great job right there. 100 points. Logan's right. Give everything a number. Step one. Now, you might see something like, then we're going to select these randomly. So this is why memorizing definitions is good, but then you want to look at like an example right here and be like, okay, does it apply? Now, you might be like, but that doesn't say they gave everything a number. But we're just taking random observations from this. You go to the registrar and you say, we need to talk to 100 students. And they say, here's a list of 100 randomly generated students. That's a simple random sample. Does that make sense? I never said everything gets a number right there, which I think maybe that some people might be like, but I didn't say everything gets a number. Well, but everything would have sort of a random probability of being selected. In a simple random sample, everything has an equal and likely chance of being selected. So this would be a simple random sample right here. Go to the registrar and they give you a list of 100 students, 100 random students to talk to. So you want to think that everything had an equal and likely chance. Just think of like one of those things where you take the ping pong balls out of it and you're like, oh, number 582, you win. So you're just having each one has an equal and likely chance. Now, systematic. Got my phone here today. Systematic sample is going to be step one what? Pick a what? Choose a random number between 1 and 24. 7. Oh, you don't get it. So quiet. Got to redo it then. Pick a random what for systematic. Really? Phone, you're acting weird today. Pick a random number between 1 and 24. Why is she quiet? 19, she said. So you are correct. We're going to pick a random starting point. Pick a random starting point. Sample every kth, which is a placeholder for what you want to use. Observation. You're just going to plug in something right there. Choosing every element of people or cookies or pizza slices or whatever you want. So, or cars, maybe working at a factory, we're going to take every 20th car and do like a stress test on it. So I always like to do the example right here. Where, example, Brian randomly goes to the library. Pick a random number between 1 and 24. The answer is 3. 3, where really wants me to go there? Brian goes to the library. Goes to the library at 3 a.m. Must be lonely. It's a song from the 90s. And talks to students about if they use the library to study. That's a horrible way to do a survey. He talks to every 20th student, has to be there a long time, entering the library. This is probably your key note right here. Like if you're looking for something that tells you it's systematic, it's going to be this right here. Does that make sense to you right there? That's going to be the big thing. If you see that, it's like, that's systematic right there. The random starting point is pretty important because you don't want to just always start at the beginning because there might be some sort of order to the process and there's complex things that could happen, but I'm not going to get into complexity. We'll go to the next example right here. But we would take every kth observation right here. So next, what do we have? I need someone to tell me another one, and this is where things get a little bit confusing. What else do we have right here? What other sort of sampling methods do we have? So where people usually get a little bit confused on the two. We have a good way of remembering which one is which. Cluster or stratified. Nice job. What type of bias can be created? I kept getting it wrong during practice. When you do systematic, just depends. That's such a good question. It's like maybe more likely. It just depends on how the question is worded. It would depend. There might be something else that they're saying they went and did. If it's like a homework problem, they might have had some other thing where they went and like talked to, they talked to like the fifth person leaving the park or the fifth person in the line for the roller coaster. So that'd be undercoverage bias. Systematic is, let me point this out real quick on this. Systematic is not going to create bias when done properly. Systematic done properly is a good random sampling method. So these are random sampling methods. Systematic done properly would not create bias. It is possible to create bias. Like if you want to understand students at UT and you only go to the library and you talk to every kth person, if I want to understand UT students, going to the library would create an undercoverage bias. Not every student goes to the library. Probably got more on-campus students and more students who utilize the library. So this would create an undercoverage bias, but it's not because of the systematic sampling. It's because I chose to go to the library. I could just go to UT and try to find every 20th student. It'd be pretty hard. I have to go. You have to probably do locations, which means we'll be doing a later one. Let's do some cluster sampling right here. So cluster sampling has very important steps right here. And let's put a note. Taking a whole bunch at once. Taking a whole bunch. Okay. So when we do cluster sampling, the first step is things are put into what? And how are they put into those? Things are put into what? This is where people make a mistake usually between cluster. They're put into groups randomly. So things are randomly put into groups. Step 2. Groups are randomly selected. Very important last step, which is going to be a key here. Very important last step. Logan crushing it right there. Perform a census on the groups. Perform a census on the groups. Chapter 7. Yeah, I think we're going to do some interpretation after this. Yep, I think that was the plan. We'll do some interpretation. So perform a census on the groups now. So this right here is probably the key defining factor where usually it's going to be a giveaway. If you see a census on the groups, what does a census mean again? What does a census mean? What does a census mean? As I write this trick question. What does a census mean? What does a census mean? Be careful. What? How did... Oh, I've got that. Haha. Okay. We get answers from everybody. So tell me, is this a cluster sample, yes or no? If you're listening carefully, you caught some stuff. Is that a cluster sample, yes or no? Is that a cluster sample, yes or no? Is that a cluster sample? Your thoughts. So we have here groups. We have domestic and international. No. So you see we have domestic and international. Those are groups. So are people randomly flying domestic or international? Is that a random assignment? Like you're like, I don't know, random domestic or international. No, that's not really random assignment of groups. We're not selecting the groups, and then we're not doing a census on the groups. We'll use this example later on, but this example is not an example of clustering. What would be a better example, better, not perfect, is we go to the airport and we select 10 flights to collect data from all the passengers on. Notice what's going on right here is that each of the flights is the cluster, and we're collecting data on every single customer on the flight. The census is when we collect data on all the passengers on the flight. So we're randomly taking 10 groups right here. So all the passengers, this is an example of clustering right here where we're taking a whole bunch of flyers at one time. Does this make a little more sense right here? Like, oh, we're taking just a cluster. We're just give me a whole bunch. You will take the whole bunch. And no difference was acknowledged. Great job right there, Logan, doing the practice, because we'll see that here for a second with systematic or stratified. Another S word. So now we get down to stratified. And this is where the other confusion is. Stratified. It's an I. I knew that. Stratified. Sampling. So when we do this, acknowledging okay. So we're going to acknowledge a difference right here. First step is going to be, guess what? You never would have guessed it. Acknowledge a difference between groups. What do we mean acknowledge a difference? Well, tell me. Is there a difference between domestic and international flights? Is there a difference between domestic and international flights? Like domestic, international, tomato. No, there's a big difference. You fly in the US, you fly outside the US. Domestic, international. So there's a big difference right here. That's not a random difference right there. That's not a flight. You be like, are flights different? Well, we're just taking a bunch of flights. We're just adding the flight. So in the first one, we acknowledge no difference. We're just taking flights, bunch of airplanes. The second one, we're actually acknowledging a difference, and we're saying, okay, well, now we want to take a certain amount. So what do we do right here? We acknowledge a difference. And then we sample randomly within the groups according to the population parameters. Good way to review this. What did Brian pretend? Brian's pretending that what percent of the flights are domestic right now? So big price difference. Oh yeah, pretty crazy, right? Brian is pretending that the true proportion of flights that are domestic are what? You try to backwork Brian's problem right here. Like if Brian wrote up this sampling plan, Brian has assumed the true proportion of domestic flights are this. See if you can backwork that right here and be like, well, I guess Brian assumed that the true proportion of domestic flights are this. Because he's going to go and talk to 120 domestic flyers out of 200. So Brian was assuming that the true proportion of domestic flyers was this, such that his sample has 120 domestic flyers in it and 80 international. So Brian assumed, and that's what this says, randomly sample within the groups according to the population parameter. So we're assuming, and if you look at this right here, Brian probably assumed that the percent of domestic flyers was 60%. Logan, you got it right there. And that's just like an assumption I made, or I'm just making it up for this problem. Well, there's 200 flyers total. And then from within that, so we sample according to the population parameter that apparently 60% of flyers are domestic. 60% of domestic people. 60% of flyers are domestic. So out of 200, we'd go right here and say if we have a sample size of 200 and we know that 60%, the probability of domestic is 60%, then we would have here that we'd sample 120. So we just take 120 equals to, we solve it first, then we write the math. And then the international flyers would be 80 right here, which is 40% of it. And this way, what Stratified does, stratifying is actually going to help to make sure we don't what the international flyers or domestic flyers. So go back to the terms we just talked about. Stratifying is going to help us not what those international or domestic flyers. 100 points on the line right here. Stratifying is going to help to make sure we don't what those domestic or international flyers. It's going to make sure we have enough of them. So it's going to make sure we don't what them by stratifying. Well, so no, it's not cluster. Remember, this is stratifying. We're not going to take a whole bunch at once right here. We're going to acknowledge a difference. Well, it's going to make sure we have enough of them. It's going to make sure we have enough of them. So it's going to make sure we don't what a certain group. It's going to make sure we don't what a certain group by stratifying and saying we need this many domestic, we need this many international. So we're saying we need to have at least this many of this group. We need to have at least this many of this group. So we're going to make sure that we have enough of those voices in our survey. It's going to guard against undercoverage. Does that make sense? So it's going to make sure we have enough of those people. So we're saying, okay, let's make sure that we have enough of those people in our survey. So we're going to not undercover them by stratifying. So it acknowledges differences to say, okay, we need representation from these groups. So when we go down here and we say, okay, we're going to acknowledge this difference, and thus we're going to make sure we have enough international and domestic flyers. Does that make sense right there? Really good practice right here on the terms. And a lot of this chapter is just practice on terminology and then thinking of examples of how it would apply. I guess got it. I think we're going to do some chapter 7. Chapter 7 coming right up. We should mention these. Last but not least, other terms, sampling terms. Okay. Other last but not least sampling terms. Let's write a problem right here. Last problem for the sampling stuff. Here we go. Brian goes out and wants to learn about golden retrievers. He takes data on 20 dogs. At his local shelter for Goldens that has 200 Goldens. Identify. He measures how happy they are by how happy really they are by tag wags per second. Okay. Identify the following. Population. Let's go sample frame, sample, population parameter, sample statistic. Who has any of the following right here? Help me out. It's got an E. I don't know how to spell. Help me out. The population is all people or things we are interested in. The population is all people or things we are interested in. I'll write out, I want you to identify for the problem while I write out the definitions. So the population is all people or things we are interested in understanding. If you'll miss some answers, it sounds like. I think you got it. Population is golden retrievers. I want to understand golden retrievers. That is my population of interest. You can call it of interest. It just means you're interested in it. Like sometimes you say population of interest. But it's all golden. Watch out, watch out. It's all golden retrievers. Brian wants to learn about golden retrievers. Brian wants to learn about golden retrievers. He's trying to understand golden retrievers. Ah, great job. So the sample frame is what? I need a definition. Help me out with the definition right here. It's all people or things we have something to sample. So the sample frame is theoretical. So the sample frame is all people or things we have what to sample. The sample frame is all people or things we have what. What word goes in this spot right here? It's all people or things we have what to sample. It's everything we could theoretically sample. Access, great job right there, Logan. It's all things we have access to sample. So, and great job, Logan, right there, 100 points again. The 200 Goldens Brian could have sampled. So, once again, everything in your sample frame, you don't have to sample. These are the dogs I could have taken data on. Does that make sense? Like the sample frame is the stuff you could theoretically sample. It's not what you sample. It's not what you want to understand. I mean, they're part of what you want to understand because you're going to sample them. But the population is all golden retrievers. And then the sample frame is the ones I could have sampled. But then the sample is what you collect data on. And what do I collect data on here? The 20 Goldens. So the 20 Goldens are what I collect data on right there. The population parameter is what we want to learn. And we want to learn the population parameter is the true tag wags per second. So So that is the truth. And that would be mu. On average, the true mean, so I should say the true mean tag wags per second. Goldens. We're probably going to get them up, right? One dog looks like my first dog. And then the sample statistic is going to be the sample mean tag wags per second. So down here on the bottom, this would be mu because it's quantitative, and this would be y bar because it's a sample. And the sample size would be n, and the population size would be capital N. Not for normally distributed, but those are the notations here. Sample frame, I don't think it has a notation. I don't know. We'd have to look it up. I've never used notation for sample frame. But those are the notations right there. That is not capital N, normally distributed. That is just a N for population size, which that would be how many golden retrievers there are. Any last questions on this? Good review of what the sampling terms are and how we go down from these terms and what they are from a problem. The sample statistic is, so it's estimate of population parameter. It gives insight into it. A population parameter from the sample data. Last two terms we should probably know would be something like a census. A census is when you collect data on everything in the population. Like the US Census collects data on everybody. What about the sample size? The sample has a size to it, correct. Sample size is N. Great question, Lakeisha, right there, 100 points. So the sample has a size to it, and so sample size here being N, sample size is the 20 goldens. And the goldens are the 20 goldens are the sample, and the size of the sample is 20. So great question. Sample size is 20, and that is the sample. The sample is the 20 goldens, and that is the size of the sample. Good question. There's one more I was thinking of. Oh, bias. Bias is anything in our sampling that pulls us away from the truth. Like if this is like a super happy golden shelter, well then that's some bias right there in the sampling. We're underrepresenting other goldens. We want our sample to be representative. So this is an accurate view of the population in your sample. So an accurate view of the population is in your sample. These two kind of work in tandem. I'll just put these on the screen here and I'll pause it. Bias and representation work against each other. So bias is going to pull us away from a representative sample. Something that is biased is not representative. Something that is representative should not be biased. But all these good terms right here. Hopefully there's not any bias in here. Hopefully it's representative. But that's got it. Good review right here. Lots of notes. Check out the previous parts. Let's hop back to the main screen. Awesome. So thank you everyone for being here, just practicing along. We're going to do some notation or some review of regression right here. So give me a second. Getting some regression output on the screen. Here we go. Let's go check it out. Regression output coming right up. So when we do a regression output, what kind of variables go into regression? Ooh, we should know this. I want to hear some blank, blank, blanking up, blank, blank. What are the conditions for regression? Who knows this? My class should be shouting it out. I made people shout out all the time when we were in person. It's like one of these days I'll get in trouble in Haslam. Never did. Thank you, Haslam, for never getting me in trouble. QQ, straight enough. No outliers, plot doesn't thicken. Let's go look at those regression conditions right here and think about what we got. We're going to predict. We'll do an easy one. We're going to do height and weight. Two quantitative variables. Height and weight are both quantitative. You can see right here at the blue. Height and weight are both quantitative. Oh, got so many pretty colors everywhere. Rows, clear, row states, gone. And so now we see the relationship between height and weight. Now, this one probably has a big issue towards the end with the straight enough. Straight enough means that a straight line goes through the data. So one way to look at it is just look right here. But what else could we look at to see if there's like a bend? What sort of plots could we look at? Who knows the answer to what plots could we look at to see if there's a bend in the data? What plots could we look at to see if there's a bend in the data? Or to see if the residuals have a problem? To see plot thickening or to see bends in the data, we could look at a what plot? Where is it? We could look at a what plot? You can kind of look at that. We'd look at a residual plot right here. See, it does give you a histogram. So I was like, this right here, how do we make a residual plot? Who knows how you make? Who can explain how a residual plot is made? Like, what do you do? What's Brian's famous saying? You take that line, you make it what? How do you turn something into a residual plot right here? That's a residual plot. And how do we turn that top plot here into a residual plot? You take your line, you do what to it? Do you see it? You see the line? You see these points right here? I'll show you these points up top. See those 2 points? Those are 3 points right there. See that point right there? It's going to be that point right there. Take that line, make it flat. That's what you do to it. So you can see right here, this is the flat line, and this is this little dash line here on 0. That's everything has a 0 residual. You can see a very positive residual over here, which has the residual of about 8 or so. And you can see it over here. You can see a residual of similar height right over here. It's a little bit lower, but it's closer to the line. So you make it flat right there. You take your line, you make it flat, then anything on the line has a residual of 0. A residual is just how much our model what's by. When we talk about a residual, like you can see the residual amount right here. Like this is somebody's actual height. Somebody is actually around 60 inches tall, but they were predicted to be around 71 inches tall. So that person, when we talk about their residual, which is like very large, the residual is about -14, which means what? What does this residual mean right here? That the model is how far away from them. Like this distance right here is about -14. When you look at the residual plot down there on the bottom, this person right here, right there, is about -14 below. If you look over here on this axis, that's how far they are below. What does that mean? What does it mean? So they were predicted to be they were 60 inches tall. They are 60 inches tall. And they were predicted to be about 75 inches tall. Or 74, rather. What tell us? It won't tell us the number there. So the model over predicts them by 14 inches. Does that make sense? The red line is their prediction from the model. We could solve it. Let's show how that's solved right here. Let's grab the equations and start doing some solving on this. So remember, they're 60 inches tall, right? So if I go here to a new Word document and I take our equation, we can actually solve for that person's predicted height. So they are 60 inches tall. We'll just make this height. We're going to write the equation in an easier way to see. They are 60 inches tall, and they weighed how much again? I need to see how much they weighed. Oh. Let's see right here. We can solve for Brian right here. Try to solve your own. Can you tell me your own residual? This is chapter 7 right here. Tell me your own residual. I'm going to solve for my residual. Brian is 75 inches tall. Brian weighs 180. What is Brian's residual? So what we're going to do is we're going to take Brian's weight and plug it in here to X. And so we go here, we plug in Brian's weight, and we are now getting Brian's what? Now that we plugged in Brian's weight, we will now solve for Brian's what? By plugging in Brian's weight, this will allow me to solve for Brian's what? I know it's that, but I want a second word before it. That is not, this won't be Brian's height. This won't be Brian's height. I know it says height right there. Let me help you out with what it is. I'll make it a little bit nicer. Well, it is height. I know it is. You're kind of right. I want a little extra on it. Can I make it do its thing? Where's my thing? Really? Well, this won't be my true... That won't solve my true height. Nope. Why won't it? Do it. Where's my equation there? Oh, there it is. Let me put something over this. Okay, so what is that? That's a little better notation now. Well, this won't be my... So no, if you... Good, this is good review. We need this review. Plugging in Brian's weight right here, we'll get Brian's what height? Plugging in Brian's weight right here, we'll get Brian's what height? What does the hat mean? What does the line do? Predicted. Lakeisha, great job right there. Predicted. This is going to solve for Brian's predicted height. So Brian is 75 inches tall. This is Brian's Y value. That is my Y value. This will solve for Y hat. That solves for Brian's predicted value of height. Does that make sense? This is Brian's predicted value of height. So we take 180 and we do this right here. And then we add to that 56.3. And then we get Brian's predicted height. Can anyone estimate Brian's residual right now? What is Brian's residual? And what do you need to remember for residual? Residual equals actual minus predicted. So I know it doesn't say actual on here anywhere, but you have to think, what is Brian's actual height? what was Brian's predicted height? So you have to think to yourself, what was Brian's actual height? What was it? Take a moment, try to find it. Try to find it for yourself also, if you want to solve for your own values. But what was Brian's actual height? What is his predicted height? What is his residual? And then what does that mean? So what is Brian's actual height? And I'm going to draw visually what this looks like while you think it over. What is Brian's residual? So the way this will look right now is the model's going to be like this. Brian's going to be over here. And Brian's residual is something like this right here. And that's my residual. And the residual is... it'd be given to you. You won't be finding those. You'd be getting the slope and the intercept. And this is the intercept right here, and this is the slope. So what is Brian's residual? So remember, we got to know Brian's actual. We got to know Brian's predicted. The way to remember residual is residual wrap. Residual equals actual minus predicted. Logan, I think that's right. We have right here Brian's actual height is equal to 75 inches. And what does this mean? Oh my gosh. What does it mean that Brian has a residual? And look visually at this. What does it mean that Brian's residual is 5.38? Here it is right here. This is the residual of 5.38. Brian is what to what the model thought? Brian is what to what the model thought? Think about, since Brian has a positive residual, it means he's above the model. Great job, Logan, right there. So what does that mean right there? Brian has a residual of 5.38. That means Brian's actual height, because this is my actual height. Sure. Compared to his predicted height. Exactly, I was 5.38 taller than the model predicted. If you have a positive residual, you are above the model. And if you have a negative residual, you're below the model. And if you have residual 0, you're on the model. Now, very importantly, we have this equation right here. And with this equation, what do we have? Interpret the slope, interpret the intercept. So interpret slope, interpret intercept, interpret r squared. Let's write out some blanket interpretations. I'm going to throw 200. Let's throw up to 1,000 points. If we can get all 3 interpretations in the chat before Brian fills them out, I'm going to fill out the blank interpretations. I want you to take a moment. You might ask me, what is r squared? We'll put in r squared over here at equal to this. R squared is shown as a decimal to start. So it's predicted to be 80 inches. So it would be not the r. Oh yeah, I think so. You're right. Great job right there, Vincent. You are correct. The residual. Yeah, so residual is actually E in notation, but the residual, I see what you're saying with R. In notation, residual is E. So you'll see that on your formula sheet. It'll say like E equals Y minus Y hat. I don't like to call it that. It's E equals Y minus Y hat. And that's actual. Great job, Vincent. Yep, you are correct. So try to interpret these right here. Try to interpret these. Be careful. Close. Oh, yeah. Great job right there. You are correct. And make sure to do context. Let's put a big bold thing right here. That is correct. But on the test, you would maybe get a half a point for that. But I think you're just putting the context I need to put. So great job right there. Some more points in the chat. So let's go right here. Context. Do not forget it. Okay, let's see. NA's got it right there. Let's do this. NA's just crushing it right there. So we got here the slope for each. I'm going to go and do this. For each 1 unit increase in X, we expect Y to increase/decrease by B sub 1 units. And that's the slope. Go a little smaller. There we go. And the intercept is, and thank you everybody. So try to do this. Yes, Lakeisha. Yeah, I think you got it right, Lakeisha. Switch it. X is, you have your X switch right there, Lakeisha. It's kind of accurate, but it'll be the X explains. I'll show that down here. Lakeisha, 100 points. We're about to throw out some big points. So the intercept is when X is equal to 0, we expect Y to equal B0. Oh, we should throw some on average on here. Some grader's going to get mad. On average. And then this is blank % of the variation in Y is explain because x does the explaining by the variation x. So I'm going to highlight some stuff here real quick while people are practicing. For each 1 unit increase in x, that's going to be underlined right there. And that's going to be underlined right there. We expect y. These are the things you need to change. Increase, decrease will be selected depending on slope, positive or negative. There's your answer to that up there. And B1 is this coefficient right here. Know that this is B1 right here. Let me write it above it. 2 seconds while people practice right here. R squared is the very exactly, Logan, and you're right there, Logan. Fill in the last little bits. That's the y value. This is B0 plus B1x. And so keep practicing. We're going to throw some big points here at the end. When x is equal to 0. So who's got my intercept interpretation? Who's got my intercept interpretation right here? I need you to fill in the blanks. Who's got my intercept interpretation? Who's got my intercept? Who's got my intercept? Let's see if anyone put it in here. I don't think anyone's put the intercept yet here. Got to go in a second. Class starting soon. But who's got the intercept? Well, be careful. Remember, use the full thing, N8. Use the full thing. Use the full thing. Use the full thing. We'll use the full context. Good practice right here. No one's gotten the full points yet. Who's going to help us get the 4 points here? 200 points each thing in the chat. I think Lakeisha just got a great job. Lakeisha right here. Let me double check what Lakeisha wrote. Lakeisha wrote 200 points for all these things right here. Let's double check. And we're just going to plug when weight, which is x, is equal to 0. We're just going to say when weight is equal to 0, we expect height to be equal to 56.3 on average. See how that's B0 right there? Great job, Lakeisha. 200 points in the chat. How about the slope? We had some people, I think you might be able to copy paste from the chat. Check your slope interpretation. Who's got our slope interpretation? We're in here in like 2 minutes. Who's got our slope interpretation? Oh yeah, no, I wrote the equation right there so you can see what the y value is. It is the y, it's predicted y, but it's still height is the y value. So what is the slope interpretation? And so you might give a little context here when we say 1 unit increase. What will be the slope? You got this. It's the practice. Look at the chat for the answers too. We know the intercept is when weight is equal to 0, we expect height to equal 56.3 inches on average. For each 1 unit increase in weight, which is for each pound increase, we expect height to increase by 0.074 on average. Yep. For every inch increase in height, we won't say, I would add in we expect or something like that. I like the expect on there. I think you get full credit. Let me double check. Oh yeah, no, you did switch it. You did switch it. The bank loan question. Oh, I'm teaching in 16 minutes, Emery. I do have email me if you can't find it. I have a video going over that. For each 1 unit increase in weight, we expect height to, but then make sure, why is it increase right here? If you can't find it, Emery, let me know and I'll send you it. So I've got some of the bank loan stuff on other videos I teach in 16 minutes. No worries. Email me. I'll send it to you. I'll try to get to that email very soon. And it's an increase because of the positive coefficient right here. You know what we can do? We can probably solve. I'm going to find. Let me find this for Emery real quick. Emery, don't leave the chat. You can actually search the channel. I think a lot of people don't know that. I can find this pretty quickly. Watch this, Emery. I'm going to send you a link in the chat. Bank loans. Here we go. Copy current time. Emery, this is for you right here. So Emery, I'm pretty good at navigating the channel. That way you don't have to worry about emailing me. Emery, that should bring you right to it. I will have office hours tomorrow, and I think we might make the videos public tomorrow when we review the exam. The last one right here, blank percent of the variation y is explained by the variation x. 35, remember to multiply the r squareds always as a decimal, multiply it. 35% of the variation in height is explained by the variation in weight. 35% of the variation in height is explained by the variation in weight. Looking pretty good. People doing pretty well. I'm going to grab some food real quick for class. But how are people doing? What are people's thoughts? Have these interpretations down. Put them on note cards. Know how to do the intercept. Know how to do the slope. All these good things right here. And also know that if you have output, you could have output. Did we do? Yeah, here it is. You could have output. Can anyone possibly tell me? This looks like jump output right here. This is our output. I'm ending with a pretty fun ending. Can anyone tell me what the coefficient of height is right here? Who could tell me? Oh, so yeah, I can mention that real quick. So can anyone tell me what the coefficient of height is right here? Like what is the, if you were to solve this model, this looks a lot like jump output down here. If you were to tell me the coefficient of height, what would it be? This looks like jump output. What is the coefficient of height here? The coefficient of height would be what? Does anyone know the correlation? So Lakeisha was asking, this would be the coefficient of height right there, because that's the estimate of the value of height. That's where B0 is. This is where B0 is at 2 seconds. Here, I'll show you. It's the same thing in jump output, because I know this is R, but it's the same way it looks in jump output. Here, I'll show you in jump output. In jump output, it'd be down here in the parameter estimates. Do you see this value right here? 0.07. And do you see it right there? That is the estimate. And do you see how it's like, it's in the same spot? It's the same table. That 0.07 right here is that 0.07 right there. That is the B1. This is B0 right here because that's the estimate of the intercept. So do you see the estimate of the intercept right here? That right there, that intercept right there is the estimate of the intercept. So if you see this output right here, this is the estimate of the intercept. So to Lakeisha's question, what would the correlation be between height, weight, and height right here? If I were to do correlation between weight and height, what would it be? So Lakeisha, what would the correlation between height and weight be? If I do height, I do weight. The correlation right here, because this is r squared, what could you do to r squared to get the correlation? You could take r squared and raise it. You could square root it, right? And guess what happens if we square root r squared? We get correlation. Does that make sense, Lakeisha, right there, to kind of quickly mention that? If you want to find correlation, you take the square root. And then why is it positive? So why would it be positive? Is because right now, height and weight, looking at the model right here, height and weight have a what relationship? Height and weight have a what relationship right now? So that's why I know correlation is positive. So I just square rooted the r squared. I took my r squared right here and I square rooted it. And I also double checked it by running it. But I know that it's positive because there is a positive coefficient. I can also see it visually. That's got a little bit of fun at the end right there with a little bit of R, but we're going to head off. If you have questions, let me know. Emery, the video's in the chat. We're going to head off. We're going to do some more work, but these concepts are very important. We got this down. You got this. Practice up. I'll see everyone in a little bit. Down to these guys. Bye for now, everyone. Bye. Puppet Shark, out. Yeah.